So I'm starting. Yeah, so from here on, the talk will be recorded. Need to press this button. Wait. Just wait. Yeah. Yeah. So let us welcome Prateek and all in this seminar. Prateek is our speaker, current. Prateek is a PhD scholar working with Professor Bhargav Vaidya at IIT Indore. Currently, he is a Prime Minister Research Fellow there. And he also awarded the SWASTi Visiting Scholar Award for a visit to SANSA, the South African National Space Agency, this year. And he's currently there in South Africa, in the Cape Town. His current research area is focused at SWASTi, which is the Space Weather Adaptive Simulation Framework, and which is a physics-based model to study the evolution of CMEs and its interaction with the solar wind when it is like going through the heliosphere. And as you can see from the title that he is currently, he is going to speak about the CME solar wind interaction using the SWASTi framework. So we are very eager to hear from him. So he got his master's in physics and astronomy from the University of Delhi. And he is also an expert in MHD simulation and Pluto code. He has presented his work numerous times in various conferences, and he's also a member of ASI and AOGS. So, well, Prateek, the floor is open for you. And regarding the questions, so we welcome smaller questions in an interactive way in between, and for like larger questions, you can ask at the end of the talk. Okay, Prateek, the floor is for you.
Thanks, Devesh. Thank you so much for providing me this opportunity to present my work at this platform in the Indus seminar series. So the title of my today's presentation is Investigating the CME solar wind interaction using SWASTi framework. And I work as a PhD student in IIT Indore, as Devesh introduced, with Dr. Bhargav Vaidya. And I've collaborated with Dr. Vagish Mishra of IIA and Dr. Debindu Chakravarti of PRL. And they have very valuable suggestions and contributions in this work. So with this, I will just quickly start with a brief motivation that why we started working on this. There are a few things that we already know about the evolution of CMEs. Regarding the governing force, we know that the Lorentz force is the governing force in the corona. And as the CME evolves and goes beyond 15-20 solar radius, drag force becomes the governing force. And we, from multiple studies, we also know that the expansion of CME is almost self-similar in the corona, and that the trajectory and the time of arrival of CME is kind of dependent on the ambient solar wind conditions. What we really don't know or have not much clarity about is that what kind of ambient solar wind conditions can bring these changes of trajectory and time of arrival. Additionally, what is the nature of the drag force that is acting on the CME front, and up to what extent it can potentially deform the CME structure, and whether the expansion of CME is self-similar in the heliosphere or it deviates from the self-similarity. And plus, an intuitive question comes that what about the internal properties, whether they get changed and whether those changes are significant or not. So with this motivation, we started working on the CME solar wind interaction. And what we basically found is that CME attains a balanced state after interacting with the ambient solar wind for a while. And what you are seeing here is assume that, or imagine a CME is coming towards you. And if you plot the drag force acting on the CME front with the color map, with this one, then you can see this features on the CME front, which is the top subplots. You can see a pattern like vertical pattern, which is gradually shifting towards the right as the CME is evolving with respect to time from 0.25 to 0.78 and from 6 hours to almost 30 hours. So you can see some patches. The colorful color map is to the positive drag force and the gray scale is the negative. By positive, I mean that CME is faster than the solar wind, and by negative means vice versa. So what at the bottom I am showing is the area on the drag force that is acting. So the green is for the positive area of the CME front where the positive drag force is acting, and the negative is where the negative drag force is acting. So you can see initially there were very large amount of area where the positive drag force was acting, but gradually positive and negative has become almost equal till 30 hours of the interaction of the CME with the solar wind in the heliosphere. By heliosphere, I mean beyond 21 solar radius. And at the left, I am showing the balanced state, which I am calling a balanced state, is basically the ratio of these area of where the positive and negative drag force is acting. So if you look at the ratio of these two, you can see that gradually they become parallel to the x-axis, which is basically time, and that ratio becomes constant after a while, almost, in these multiple cases. So now let's dive deeper into how we did this and how we came to this conclusion and what are these cases. So let me introduce the SWASTi framework, which basically stands for Space Weather Adaptive Simulation Framework. And we developed this with twofold motivation. One is the forecasting of space weather macro properties like the solar wind, stream interaction region, arrival time of CMEs, etc., and assessing or using this model to study the solar wind, the stream interaction regions, the CME evolution, and the main focus of today's talk, that is the CME solar wind interaction. So coming to the ambient, to the solar wind, I will just briefly go through the model that we have created for the ambient part of this work, that is the solar wind. So it employs a semi-empirical coronal model based on a modified WSA relation. And in the beyond the coronal model, that is up till 21.5 solar radius, there is the MHD environment, which is the inner heliospheric domain, and that is based on Pluto code. Basically, the ideal MHD module of the Pluto code. Those who don't know Pluto code, it is basically an astrophysical MHD code, which has a very variety of different modules like ideal MHD, resistive MHD, relativistic MHD, and very versatile domain of the physics that you want to address. It is also having adaptive mass refinement. So there are tons of everything. It's a very versatile code. So depending on the user's choice, they can opt and make their own domain or the model. So currently, this solar wind model takes around 5 to 6 hours to run on a 48 core computer. So if you solve this SWASTi-SW, which is the solar wind module of SWASTi framework, then you will get plots like similar to this one. So the first one is a 3D plot, where you can see the 5 is going from 0 to 360, and the theta is basically from -60 to 60. You can see for the R theta plane, it is going from -60 to 60. And in these plots, the radial the space is from 0.1 AU to 2.1 AU. That is covering the areas of Mercury, Venus, Mars, and going beyond Mars. And the bottom is basically the match of the simulated profile at the Earth's location with the Omni data. The blue is for the MHD simulation and grayscale is for the Omni data. And you can see it's a quite decent and very good match for this particular CR, which is CR2104. Additionally, with this solar wind module of SWASTi, we can also use it to study the stream interaction regions. And I will just quickly talk about the Aditya perspective of this, which we actually did with the aspects. So we all know what is a stream interaction region. It is basically the compressed region between the slow streams and fast streams. And in particularly, there is some traditional technique, traditional definition of the SIRs, which is basically based on the speed of that region, magnetic field magnitude, and the density of that region. But once we saw the aspects and tried to simulate its potential observations based on its resolution in the angle or span in the longitudinal and latitudinal directions, and we tried to compute the average flux of proton in the theta and phi direction. So we noticed some peculiar properties which were happening in almost every SIRs, which is basically, if you look in the theta direction, it is going down and again up, and in the phi, it is flipping around. So this feature was common in everything. And that is the one thing that we can, once the Aditya data comes, we can explore further and see to validate this thing, that whether adding these two properties can make the SIR detection more robust. So that was about the ambient, the background. Now let's come to the main transient, that is the coronal mass ejection. So to simulate this one, we use coronagraph images to for the input properties of the CME, like the structure, half width, tilt, these things. And currently we have the cone and flux slope models of the CMEs, and the time cadence, the frequency that which at which we can store the data in the simulation is 5 minutes or even lower, like 3-4 minutes also, which is pretty much at the almost the same rate at the observation. So just to demonstrate how the flux slope model, it's a movie. So our flux slope model is based on fried CME geometry. It also has magnetic field components, all the three, and it incorporates some complex geometry, the deformations, like flattening, pancaking. So these are possibilities. If somebody wants, then they can incorporate. And currently, we are taking a homogeneous density and homogeneous temperature of the CME for simplicity. So if I let this movie run, then you can see that the CME is expanding gradually and it is moving beyond 0.1 AU. And as it is moving similarly beyond 0.1 AU, I'm storing those values at this interface, and that is going inside the simulation domain. And with time, hence, a proper CME structure will get formed inside the MHD environment. So with this solar wind and CME module of the SWASTi, we try to study the CME solar wind interaction. And the one approach with which we moved forward is with two case methodology. One is the real case and one is the synthetic case that I will be talking about in the rest of the presentation. So the real case is the default setup of the SWASTi framework, having the CME and solar wind. And the synthetic case is a hypothetical case where we have deliberately kept the initial solar wind constant, and hence it evolves almost in a constant fashion. And you can see this one is, the green one is the solar wind speed from 0.1 AU to 2.1 AU, and you can see it's almost having the same value. So it's a hypothetical case. Same with the density, hence as the speed is almost constant, the density almost becomes constant, and the magnetic structure is having quite a nice dipole structure, which is not true in the case of the normal solar wind. You can see it's quite complex. There are SIR regions in the density plot, slow wind speed stream interaction regions in the speed plot. So in reality, there are fast streams, slow streams, varieties of them, and plus strong SIR regions, low SIR regions, and a complex magnetic field configuration. So we chose a synthetic case. The reason of choosing was that let's evolve the CME in a simplistic hypothetical scenario and compare it with the real scenario and see what the differences is arising in those two CMEs evolution. Because the differences that arises in these two CMEs, that is corresponding to synthetic case and the real case, will basically reflect directly the effects or the impacts of the anisotropy or the inhomogeneity in the solar wind. That is mainly due to the interaction regions and co-rotating interaction regions. So with this, this is the snapshots of the simulation. Here I have shown the scaled density just to make sure that the SIR regions are very clear. So the scale density is basically density by R square. So this density gradually decreases by R square. So we have multiplied. So you can see that the SIR structures are very clear here, and the pink structure is basically the 3D CME structure which is being traced. Now the tracing of the CME inside the simulation is also a tricky part. And for this, we have used a tracer technique. It's a passive scalar technique where the tracer is being solved as a simple advection equation. And as the CME was inserted inside the simulation domain, the tracer was made the value of 1, and everywhere it was 0. So as it was evolving, if we just plot the tracer value, we can see where the CME and how the CME is looking. So you can see here, these are basically the tracer values up to the maximum threshold that we decided to define the CME structure. And this 3D structure you can see very nicely, which is isolated from the whole thing in a colored manner. So what are the few things that can be concluded from these time snapshots is that initially, if you see, the CME is very nice in a curved fashion. And as the CME advances radially in the heliosphere, you can clearly see the deformation is happening. And you can see that the high density regions are getting formed at the SIR when the CME is interacting with the SIR. And plus, the texture is also becoming coarser when the CME is interacting with the SIR and is smooth elsewhere. So it basically shows the interaction or the nature of interaction of CME with the SIR or the ambient solar wind, and it can indeed make it compressed and deform as it evolves in the heliosphere. So to dive into deeper into this thing, that the evolution of CMEs, let's take the slice of the CME structure also, and let's plot the speed profile of the solar wind and the contour line of the scale density. So these are the scale density contour line, and this is basically solar wind speed has been plotted. And this is the slice of the CME's 3D structure in the ecliptic plane. So you can see the high density regions forming at the front of the CME, and specifically when the CME is interacting with the SIRs, you can see these black structures. This is forming here and gradually here. So it's quite clear that the CME gets deformed. It also, when it is going just inserted inside the simulation domain, it is gradually, if we look carefully, it gradually glides across the SIR. And we intentionally inserted the CME across the SIR to see the most of the changes it can see if it is going through the SIR. So you can see it is slightly gliding towards it, but again it regains its shape. And due to this top flank, as it is inside the fast solar wind space, it is overexpanded as compared to the bottom flank, which leads to the overexpansion of the top flank and underexpansion of the bottom flank. And interestingly, you can see that the density regions here was not much, and once it started interacting with this SIR, the density regions are more. And the nose position, that is the topmost apex of the CME, the density was highest at this point, but gradually as the other parts of the flank started interacting with the SIRs, the density was there highest. So we dive deeper into this by calculating the volume of the CME. Till now, I only talked about the qualitative part. Now we get into the quantitative part, that what about the values? What about the percentage? What are the values that is getting evolved? So if we talk about the volume, since we were able to isolate the 3D CME structure, now we can compute the volume of the CME and see how it is evolving with respect to time as it is propagating in the heliosphere. So here what I have plotted is for two Carrington rotation periods, 2165 and 2238. And there is red one is for real case, and the green one is for synthetic case, the hypothetical case. So you can see that the CME is almost following power law kind of evolution beyond certain point. But one can say that it might be going from here or might be following power law from here. But to draw that ambiguity, we can plot the slopes of this power law behavior and exactly see when the power law behavior is attained. So if we plot the slopes, the alpha value, d to the power alpha, you can see that beyond this point, which is approximately 40 hours, not exactly, but if we want to divide these into two states, that the 40-hour estimate would be a quite reasonable one. So beyond 40 hours, you can see they are almost a parallel line, means they are following indeed a power law beyond this 40-hour evolution. So from this, we can say that there is something happening beyond 40 hours, which is not earlier, and now the volume is following a power law. There is some difference in the before and the after state. So this led us to the examining the nature of the drag force that is acting on the CME front, which I showed in my one of the earliest slides. So this is the evolution of the drag force on the CME front. And you can see if you go beyond 30 solar radius, now it's not necessary that where the initially it was positive drag force, it will remain positive drag force. No, rather it's very dynamic. Sometimes it's positive and sometimes it's negative. Basically, it's the interplay between the relative speed of the CME and the solar wind. Sometimes CME, the solar wind is pushing the CME because CME is having greater speed, and sometimes solar wind is pulling CME because it is having greater speed than the CME. And it's a localized effect. But overall, if you see that beyond 40 hours, it is achieving a state where the area of positive drag force is by the area of negative drag force is become a constant. It's not that the areas are same, otherwise the CME will stop. It is going forward, but the ratio of those two areas become constant on the overall the perspective of the CME front. But if you look locally, the things are changing, but the changes are getting compensated elsewhere and the area remains the same. So if you see the distribution, it is kind of skewed normal distribution. With respect to time, it attains into that shape. But the overall shape or the interaction of the CME with the ambient achieves a balanced state, but locally they are varying and having a dynamic nature. And this balanced state is approximately being achieved after 40 hours of the CME evolution. The reason why I'm every time mentioning hour and not focusing much on the radial distance or the radial evolution, because we notice that if we talk about the temporal evolution, that makes more sense as compared to talking about the radial evolution, because the interaction is basically governed by how much time they are interacting, the CME and the solar wind, rather how much the CME has evolved. So basically the interaction can be defined or studied in a better manner if we talk about the temporal evolution rather than the radial. But if you look at the radial evolution, also we'll get the same thing, but not with that much of smoothness, rather some fluctuations. So that was about the volume evolution that it was following. What about the properties, other properties of the CME, like the thermal pressure, magnetic pressure, the temperature, density? So if you talk about the distribution of these properties, internal properties of CME, so what I have plotted is the median of this distribution. So if you look at the CME structure, there will be a distribution of these properties. And if I take the median of those distribution and see how that median is evolving, I can comment on the whole distribution, because median is the thing that can talk about the whole distributions one statistic perspective. So I have plotted the median evolution. You can see this one is the thermal pressure. This is magnetic pressure. This is speed, density, and temperature. And again, the green one is the hypothetical case, and the red one is the real case. So you can see that the red one, the median of this distribution of the thermal pressure for the red one is higher than the green one. And again, if you look at the speed one, the speed of the hypothetical case, it's kind of achieving a threshold value. It's kind of getting a truce with the solar wind. It is achieving a zero acceleration state where the speed is almost beyond which it is getting almost constant. But that is not the case with the real case. And this was kind of intuitive, because in the hypothetical case, we assumed everything to be homogeneous, isotropic, whereas in real case, it is not. There are inhomogeneities. And that inhomogeneities in the solar wind, which is the presence of low, high speed and extreme interaction regions, is basically keeping that speed going down and down in the case of real case. And because it is getting more force sometimes, sometimes lesser force, due to which the volume expansion locally is also changing. So that's why the whole distribution of that one is changing. If you remember, I showed the top flank was overexpanded and the bottom flank was not. Hence, the distribution is getting affected very much in the case of the real case as compared to the hypothetical case. Now, if we talk about the alpha, just to check whether are they following a power law, because it sometimes seems that they are following a power law, especially for this green line. If you see, it seems to be a straight line. But if we assume it to power law and then plot the value of alpha with respect to time, and if it doesn't come parallel to the x-axis, it is not a power law. Rather, it is not a strict power law. So you can see it's not behaving like a power law strictly as the volume. Basically, I'm talking about the median of the distribution of these properties. But in some cases, it seemed to behave like a power law. For example, for this case, this is for CR223. The earlier results were for CR2165. So it shows that there are not very fixed trend in case of the distribution of these pressures. they do get changed, but whether they follow power law, that cannot be generalized. Though we have only did study for 2 CRs, but only in those 2 CRs we are seeing the ambiguity. So that makes it that it is not a generic thing to conclude that it's a power law. But volume does show a power law. We have seen it. So this brings me to my summary slide. So what we summarized after doing this study, that the main uh, point in this interaction of CME and solar wind is basically the degree of anisotropy or inhomogeneity present in the ambient solar wind. If the degree of anisotropy or inhomogeneity is more in ambient solar wind, the interaction will be more or of higher degree. The changes will be of higher order. But if this inhomogeneity is lesser, it is more homogeneous, then the impact of ambient solar wind on CME will be more even. And this, obviously, this degree of inhomogeneity is bringing a dynamic nature in the drag force, which is, and by dynamic nature, I mean that locally it is very varying. It is not constant at every part of the CME front. Sometimes it's somewhere it is higher, somewhere it is lower, and that is also changing with the string in the front is also changing. And that brings the non-uniform deformation of the CME front. The CME front does not remain very uh, in a curved-like fashion, rather it is getting deformed and in a very dynamic manner. And the expansion is not self-similar because we are seeing there are deformations, yet it is following a power law after attaining a balanced state. So we can say that it is a two-phase evolution. In the first phase, the CME is interacting with the solar wind and it is trying to attain a balanced state. And after a while, it makes a truce with the solar wind and it is having a nice balanced state situation where it is evolving following a power law behavior as far as expansion is concerned. And the internal properties of CME, they do get impacted significantly, especially when there are a high degree of inhomogeneities present in the ambient solar wind. So with this, I will stop here. Thank you. Thank you very much for your time.
Yeah, so it is really a very good presentation, Prateek, and also I like the slides they are really beautiful. Thank you so much for your presentation. So as I can see that there are few questions in the chat box. So so if the audience wants, they can also ask him like using their speaker, like mic. Otherwise, I will just read them, or otherwise Prateek can also read the questions from the chat box, as I think you can also see, Prateek, right?
Yeah. I'm looking at it. Does the expansion of the CME laterally also introduce? They'll expand it. Yeah. The more drag force with the solar wind. Okay. Yes, the area will increase, and the drag force magnitude does depend on the area. So if the expansion is more, then the value of drag force will indeed increase. Yes, that I think that will be true. For more expansion, the drag force will be higher. But as the expansion is becoming more and more, or the effective area is increasing, the speed of CME and the speed of ambient is also decreasing. So effectively, in reality, if it is happening earlier, beforehand, very close to the area, then it is good. But I don't think that it will always be true. Okay, I think Satabdo can unmute himself. I can ask directly.
I think Shatabdo is in the bus, so he might not be here. Yeah.
Okay. Yeah, Ritesh also has a question.
Yes, so actually I was referring to the paper by Shatabdo itself. So maybe you may have already talked to him regarding the volume expansion of CMEs. And I guess you are working on the heliospheric part. What we did was in the inner coronal, like
Yeah, yes.
corona region, and it will be very interesting if we can like complement these things with observation and
Yeah,
simulation.
yeah,
Looking
yeah,
forward to it. Yeah.
yeah, sure. That's very interesting aspect that we can surely look into it.
Yeah. Okay.
Okay,
Yeah, so
Anvesha
there
has a
is,
question regarding
yeah,
the disconnecting the legs, pushed or disconnected in between. Oh, okay. So, so first of all, we are disconnecting the leg in almost the similar fashion that you did. We are disconnecting it when the ambient solar wind has the CME speed, or the leg of the CME has become of almost the same speed as the nearby solar wind speed. So then we are cutting it. So it's not like exactly we take the average value around the CME's foot points, and then take their nearest reasonable value, like 450 or 400, like this. And the whole CME flux rope is not getting pushed as a continuous body, rather discrete, but it is getting inside at each time step. So basically, it's continuous in numerical sense. So there is no gap in DT where the flux loop is not getting inserted. So it makes it a continuous body once it is inside the heliosphere. And does the initiated CME have any component of radial velocity normal to the elliptic plane? Yeah, it does, because the CME is expanding. So there is like toroidal speed and there is poloidal speed of the CME. So it does have, and plus once it is inside the simulation domain, so it will obviously expand based on the gradient of pressure. So it will have all 3D speed, velocity vector. Did the filament originated CME and the fluid? Oh, okay. So I don't know that. I've not looked into it, whether the CME was associated with the filament or not. That may be a good way to look into this, but I've not done that, so I won't be able to say on this.
there is one more question from
Yeah, so yeah, that's a very nice question. So it's not T to the power 3. We only did for two cases, CR 210, 2165, and 2238, and plus there were real case and hypothetical case. So we had four cases with a different ambient situations. So if it is a self-similar expansion, then it has to be close to 3 and not much variations. But what we saw is that it is going from 3.2 to 3.4. So, and plus we are not saying it's self-similar expansion just because we are seeing the deformations that the symmetry is broken. So it is not getting expanded in the same proportion. Rather, somewhere it is expanding more and somewhere less. So that's why we have concluded that it's not following a self-similar expansion. Rather, it is power law, but not self-similarly expanded one. Yeah, it's non-fractal power law, we call it. How does that
how long does it take to simulate the entire thing?
Entire thing. Oh, the entire thing plus CME, everything will be over in 8 to 9 hours, even less. So for CME, what we do is that we solve the solar wind up to a state where we have achieved a steady state. So you can say it takes around 4 to 5 hours to do that. And plus CME, so simulating CME doesn't take any extra time. It's like that. So based on the time when the CME was injected, we'll have to inject it at that time, because we have to wait till that solar wind stream comes near that, because we solve in the current and longitude frame. So that depends. So basically, we can solve everything. The worst situation will be of 9 to 10 hours. We will have everything in good enough resolution, or rather medium resolution.
And I think she has also asked what are the limitations of SWASTi, if there is any.
Okay, the limitation right now would be that we don't have AMR. We can look into AMR. We don't have magnetic reconnection. We don't have temperature anisotropy. We don't have many things. But the point is that, are they important if we look at the macro properties? So if we look into different things, then those things might become important. But I think having temperature anisotropy will be a good thing to add. We can do AMR. We have not done it, but we can do it because it's in the Pluto. And plus, we can also look for resistive MHD that will allow the magnetic reconnection. And then we can see whether that CME, when it is evolving, and then it is whether the reconnection is happening with the ambient solar wind, that flux cancellation is happening.
Hi, Prateek. I have a question. Okay, so have you thought about shock and SIR interaction? In this case, usually CME will be accompanied by the shock most of the time. So, how would that affect your study if you have a shock in front of a CME?
Okay, so if we really want to look into the shock, then I think I will have to go to higher resolution, or maybe AMR will be the best. Then the sheath region will be very nicely simulated. In this simulation, the sheath region is not very, very dependable. I won't really find it reasonable to study the shock with this resolution. If we increase the resolution, then we can do this study. But I think, yeah.
Okay, you need AMR for that. Yeah, that is true. But in terms of like observational aspect, also, like you might have had many in situ profiles which has shock and SIR and CME combinations also. Yeah, maybe observational study also could help some things about these properties while interacting, right? SIR and CMEs.
Yes,
but
yes.
Yeah, it is very limited observations.
Yeah, for
Multi-point
2165, there are in CR 2165 there are 5 halo CMEs, and we did the simulation of each one and validated with the observations. We were having very nice time of arrival with maximum error of 5 to 6 hours. So it basically depends how much good initial properties we are deducing, because that matters a lot. The magnetic flux value, whether that is accurate or not, the tilt value is accurate or not. So these things matters. So if the initial input parameters is of having very high confidence, then I think the arrival time and the in situ properties will match very accurately. Not like very accurately, but it will be a decent, good enough match to trust.
Yeah. Thank you.
Yeah, I think there is one unanswered question by Ashwin. I think he asked in the beginning. Yeah. So the question is, how can we neglect its presence and correlate the drag with the solar wind, the speed alone? So if you see this question is after those question. Yeah.
So how can we neglect the presence and correlate drag with the solar wind alone? Maybe I'm not able to. If Ashwin is here, I would like really glad if he asks himself.
So Ashwin, if you can just ask him. And Ranodipta also wanted to ask something.
Yes, I have a question regarding the CME attaining the pressure balance state with the ambient wind. So mostly when we do the GCS reconstructions of the CME, in the inner corona, or like I don't say that for all the CMEs, but most of the CMEs we see that around 10 to 15 solar radii it reaches the pressure balance state that mostly behave like a self-similar. But like when we but there is a like problem like in the when we do this insertion thing, inserting a flux rope through the heliospheric inner boundary, then that we see also in the euphoria set that the speed in which you insert the CME at the lower boundary, that is but that is much way lower than the speed that we see at the inner boundary when it is already launched, because that is due to the over expansion. The initially the CME show the over expansion at the inner boundary, and which is basically I think the issue is the pressure balance condition, because like we cannot set up a realistic density or the magnetic field inside the CME during the insertion beforehand, because we don't know what amount of like exact density or pressure would behave the CME like a so that it already in a pressure balance state while launching it through the inner boundary. So I think there should be it's still bit a insertion problem when you look at this matter, that at what distance the CME reaches at like the pressure balance state. So would you like to comment anything on that?
Yeah. So it's true that the insertion is not very natural, because at 21.5 the CME would have formed its own shock waves and the sheath region. But when I am injecting the CME, it is not having those things because I don't know those properties. One way maybe to estimate those properties and then insert in a more organic manner, such that it is having those properties in while insertion. And for defense, I could only say that in the if you look at the state from which this transition happens of the nature of the governing force, like in the coronagraph images, if we look at 15-20 solar radius, so people believe that that stage is where the Lorentz force is mainly governing the dynamics, and beyond 15-20 the drag force starts. So what I thought that maybe even if the solar wind is there, due to the Lorentz force is the governing force, it won't be affecting much. And once the drag force becomes the governing force, then gradually that thing will start shaping. So basically that transition is between 15 and 20. And from there, it will start deforming and these things will become. So because our this inner boundary is at 21, so I thought it is like reasonably good enough to estimate that from this point, the CME will start feeling the pressure, the drag force in a governing fashion rather than before it. But this is really like a arguable statement. It might be at 15, it might be at 14. So something like that.
Okay, thank you.
Yeah, thank you.
Prateek, I have a
So,
question.
yeah,
Can
you hear me?
Please,
Hi,
please go on, Chitradeep. Yeah.
Can I go ahead?
Yeah, sure.
Okay, thank you. So, although CME modeling is not my primary domain of research, somewhere I read that you see larger expansion in this poloidal plane compared to toroidal plane, as evidenced in some breakout models and in some observations. So, is this the case that you see in your simulations also?
Can you repeat again? In which plane do you see more?
So you see elongated expansion in the poloidal plane compared to toroidal one. Sometimes the ratio can go up to 4:1 or 6 or 8:1, as reported in some review, living reviews. So is that a case? What you see in your modeling also?
Okay. Just to be sure that I'm understanding it well, by toroidal you mean by poloidal you mean phi direction or theta direction?
R theta. Poloidal means R theta plane, and toroidal I mean
R theta plane.
phi
Okay.
plane.
So if poloidal is R theta plane, then what I think in most of the cases in R theta, in R theta it will be more in poloidal.
More expansion.
Yeah.
So in your simulations also you see this kind of effects.
Yeah,
Okay,
because
okay.
what happens, the reason of that is, if you look at this plot, this plot, if the CME is like this, this is structure, let's say beyond 30 it is going, then beyond 30 is very fast, and the variations of the slow is in this region. So the part of CME in these regions are having a totally different nature of the drag force. The CME are very fast, and they kind of compel the CMEs to like go in these directions. The expansion in this direction, I see them more as compared to in the same elliptic plane.
Right, great. Thank you. It was a great
So
talk.
it will depend on the angular height of the CME as well. If it is smaller, then that is not going to be the case.
Great. Thanks.
Yeah. So Prateek, I have a question.
Yeah.
So you mentioned about this positive drag force thing, no? So that's the ratio is being constant after 40 hours, right? So so I just want to ask you, so can you comment on the fact, so in the drag force law, like where you have this FT, the drag force, which goes as rho v square, and there is a constant there. So in the estimation of the drag coefficient, so can you comment, like if we can have any light regarding the estimation of the drag coefficient using this particular thing, that the after like 40 hours, the cross-sectional ratio regarding the drag force is being constant or something like this. Yeah.
Yeah. So in my study, what I did is that I took the drag coefficient to be 1 for simplicity, that just to make sure that is not in the picture. I took it to be constant, and then I simulated everything. And the ratio that turns out to be constant is the area of the positive drag force, the ratio of area of positive drag force to the negative drag force. Yeah. So if we want to relate it to that, because in the balanced state, in these ratios, the area of CME, the total area of CME doesn't matter. So I think in the drag force equation, the area of CME front comes, not rather the area of the positive or negative. So I think
the cross-sectional area actually comes.
Yeah. So it should be independent of the variations of that one. Though this 40-hour mark may vary, obviously, if the value is not 1, but the conclusion will not change. It's my thinking that if we change the value of this coefficient from 1 to, let's say, 0.5, or we vary it in a dynamic manner that it goes beyond the value is changing, even then there will be attainment of balanced state after a while. But yeah, that is an interesting thing to look into it, because taking it 1 is an approximation. In some studies they might call it's a crude one.
Because the thing is that what I know from the drag model is that, like the drag coefficient, the C actually. So this, although this is not always directly related to the area of cross sections, because in the equation you see this Ft equal to C into A into rho into V squared. So A is there, but I think A is there. So but like in some of the works it has mentioned that C can also like vary on the basis of the area of the cross section, and also like in the material, like in a sense the material, the plasma of the CME.
Yes,
so
basically,
so you can look into this. The second question I want to ask is, so you have mentioned that the volume is also like after 40 hours is basically kind of fixed to a particular trend, right? So I just want to ask you, so is rearrangement of magnetic field lines play any role in this volume, like being fixed in a kind of trend after 40 hours?
Okay. So I have not particularly done that by taking different orientations of magnetic field and checking whether this is happening or not. But in an indirect way, we can answer this by saying that these are median, but I have plotted the real values of the thermal pressure and the magnetic pressure. The thermal pressure is quite dominating as compared to the magnetic pressure. So even if we change the magnetic orientation, so we are basically changing the magnetic pressure in a sense. But because the thermal pressure is more, I don't think there will be any significant changes if we change the magnetic orientation. But to really answer that, I will have to see by doing it that whether there are any changes. But intuitively, it doesn't seem to show any significant change.
Okay, because the thing is that it comes into mind because since CME usually follows a flux flow kind of structure, and like unfolding of magnetic field lines, it will enhance. It is like acting in a way that it will enhance the volume. So it can. I'm not sure. So like
Okay.
you can look into this. Yeah.
Yeah, sure. That will be
Yes.
interesting thing to look into it. Yes.
Yes.
Having different magnetic orientation and see that whether they are affecting the volume of the CME in the
volume.
heliosphere.
Yes. Yeah. So I can't see any other question in the chat box. So if you have any question in the audience, so you can unmute yourself and ask Prateek. Otherwise, you can also raise your hand. So
Devesh, there is a question by Aswin, if you could read from the chat.
yes.
Arpit has also raised his hand.
Yeah, Ashwin. Okay, so first I'll read Ashwin's question. So in your simulation, did you also include the volume expansion of CME introduced by the drag along with the SW drag? So this is his first question.
So I am not including volume expansion, rather the CME is getting expanded on its own, depending on the pressure gradient and the MHD equations. So I'm not like doing it myself, rather in the MHD equations, the CME is behaving like that. So I don't know whether I was able to answer that question, but if included, at which point did the expansion stops? If it stops, there will be a change. Okay, so that is related one. So I'm not like doing it manually, rather the CME is expanding on its own following the MHD evolution.
Yeah, so I think Arpit has raised his hand. So
yes, am I audible?
yes, please.
Yeah, Prateek, can you go to the slide where you have shown the what are the signature we will see with aspects of SIR?
Oh, sure. Yeah.
So I wanted to know whether we see these kind of signatures with previous instrument, or there is a special there is some unique ability of aspects which will enable us to see these kind of signatures.
Yeah, so actually, I looked into the literature. After 1971, this Belcher and Davis, no one has showed it through the observations. I may be wrong. I was not able to find it. Recently, Yogesh, student of Devendu, has published this using the this data of wind. So only wind is having this multi-directional observational capability, and the aspects will have even advanced multi-directional observational capability. So yes, these things are getting observed in the wind by like 500, 300 SIR features recently published. And with aspects, we'll be able to conclude in a more better way.
Okay, thanks.
So if anyone want to ask, he or she can unmute and ask.
Hi, Prateek.
Yeah, hi.
So you have only minus 60 to 60 degree in theta plane, right? I mean, in your Pluto code. So is it? I mean, Pluto itself has that only that capability, or it has that option to just only choose that area, or
No.
it can resolve the polar also.
Yeah, the Pluto can resolve the polar also
Okay.
using some techniques if it is getting unstable. If it is not, then it's fine. But generally, it does at the poles, it becomes a little tricky. The Pluto only solves the MHD equations for us in different coordinate systems like Cartesian, spherical, or this one, cylindrical. What we do is that we have constrained ourselves from minus 60 to 16. The reason being that we have lesser number of grid points to solve. Nothing very interesting is happening beyond plus minus 60. We cannot validate with the observations, and plus it will slow down the total numerical time it is taking to solve this thing. So we have constrained ourselves to that. If we want even faster and maybe more, we can go to 55, 50, maybe 40, but it depends on the user, what he wants. If it is only interested in 0 degree, he might not go even till 60. He will be like shorter. So it depends on the user, basically. But in Pluto, you can, yes, obviously go from minus 90 to 90 and solve.
Okay. Thank you.
Thank you. Okay.
Prateek, hi. Hello.
Yeah, hello.
Yeah, so I just want to ask you another question. So, so usually it is considered that the magnetic field is like kind of it comes from the flux conservation. So basically, when it when the CME goes and moves into the heliosphere, expands also, like it should follow like 1 by r square kind of structure, because if you see that B dot A equal to constant from the conservation of flux. So like I just want to ask you what you see if you plot the magnetic field as a function of like time, like elapsed time in a sense. So how do you see, is this following the same trend, or if it is not, like?
Okay, so you're talking about CME, not about the solar one.
CME, yeah, CME, yes.
Okay, so I have not seen that specifically. I know about solar wind. It generally goes as dipole if anybody wants to like formulate it, but I have not checked for CME. That's an interesting thing. So you are saying that how it will be varying around the CME central axis, right? Okay, so around the CME central axis, so it's a tough thing to answer. So I don't know whether it will go by 1 by r square or 1 by r cube. But so it depends on what formulation that we are taking. Maybe I'll just run this movie. Yeah. So I think there is some issue with the movie. But you can see that in this plot, if we look, then we can see what is happening around the central axis. But I have not like formulated the what will be the analytical solution, whether it's 1 by r square or 1 by cube. But rather there is a solution of that. It is based on whether you are taking Lundquist model, Goldhall formulation, how you are shaping your flux ropes. That will depend on that. So that can be calculated for sure, but I'm not checked whether it's 1 by square, 1 by r cube. Yeah, I have not checked it.
No, it's yeah. So Yeah, so I guess there are no more questions. So then we can end this talk. So basically, a big applause to our speaker. It's a very, very nice talk and a very, very nice work also. And like, it's great. Yeah.
Thank you. Thank you so much.
So,
maybe let's
now we can-
virtually clap for Prateek once before we end the recording.
Yeah, I'm doing clap.
Nice. Very nice
Yeah,
talk.
thank you
Prateek.
guys. Thank you so much.
Very, very, very good. Yeah.
I will see you.